Okay, starting off with graphing now, moving on from substitution, we talk about how graphing generally works. Again, like I stated before, graphing is not really the best way to solve systems of linear equations or systems of equations in general, because I think it just takes time because you have to draw the graph out like this. You have to plot it, draw a line through it, draw another line through it, and find the intersection. And by the time you plot everything, that wastes a lot of your time. And considering that AMC is on average 3 minutes per question, it's very hard to get this done within that short period of time. And like I said, graphing is not useless. Of course, it is very useful when it comes to finding the number of solutions to some sort of intersection. But right now, for solving exact values for systems of equations in general, graphing is not the most feasible method. However, we'll look into the same example that we did for the first one, and which was x minus 12y is equal to 2 and 3x plus 6y is equal to 6. We're going to use the same example and show how the graphing gives us the same solution as last time. And so here's the graph of how it looks. And we have that. So we would rewrite x minus 12y is equal to 12 is equal to 2, my bad. And we would have to graph that part out, which is obviously this equation, x minus 12y is equal to 2. And then the other equation, 3x plus 6y is equal to 6, is this equation. You draw both of them out, you get an intersection at 2, 0, and then you get your answer. But right now we have the graph in front of us, so it looks easy, but graphing this entire thing is a really big headache. And I think that's why you would be better off if you used Gaussian elimination, for example, for this question, even as opposed to, for example, substitution. I think Gaussian elimination really helps out when there's simple two equations to solve that can often kill off a variable. Also, we'll cover this a little like in sort of tips and summaries section, but in order to avoid fractions, oftentimes Gaussian elimination can be very useful. And graphing can be difficult in that front because the slope of this, for example, x minus 12, y is equal to 2, happens to be positive 1 over 12. And so it's not very easy to graph this out. And last but not least, our powerful symmetry. So talking about symmetry, let's go with this problem, which really demonstrates how symmetry works. I think right off the bat, a lot of you can see how we're going to kind of use symmetry to our advantage here. So let's start by noticing what we have in these equations. One thing we know is all of the equations have 4 variables each. And one thing we realize is obviously that means it's missing one of the variables. And one other thing we realize is that, so this one is missing E, this one is missing D, this one is missing C, this one is missing B, and this one's missing A. So each variable is missed once in the entire set. So I think that's a nice bet. What we could do is take advantage of the fact that it's so symmetric, that each variable is facing the same behavior in some sense. So what we're going to do is we're going to add up these equations. So we have each variable occurring 4 times in the set of 5 equations, obviously because one of the equations doesn't have that variable. So when we add this up, we're going to get 4a plus 4b plus 4c plus 4d plus 4e is equal to 4 plus 8 plus 12 plus 16 plus 20. Okay. So now you're going to factor out the 4. And you're going to add up the right-hand side. So 4 plus 8 is equal to 12. 12 plus 12 is equal to 24. And 24 plus 16 is equal to 40, I believe. And 40 plus 20 is equal to 60. So our right-hand side would be 60. And we're going to divide both sides by 4. So what we get out of it would be a plus b plus c plus d plus e is equal to 15. How is this useful? Looks completely useless. Maybe let's work it out. Okay, so what they're asking is they're asking for a, b, c, d, e. And we have a sum of all 5 variables. So one thing I realized is that, like I said, each variable over here, each equation over here is missing one variable. So what if we took this equation, like equation 1 that I labeled as, and subtracted the other equations one by one? So I'm going to name this equation 2, 3, 4, my bad, 5, and 6. All right. And I'm going to subtract 1 minus 2. And I would basically get a is equal to 15 minus 20, which is equal to negative 5. Because it's a plus b plus c plus d plus e minus b plus c plus d plus e. So you just have a. And if you do a similar process, you get that b is equal to 15 minus 16, which is equal to negative 1. And you get that c is equal to 15 minus 12, so that's 3. D is equal to 15 minus 8, which is 7. And last but not least, we have that E is equal to 15 minus 4, which is 11. So our final set actual answer would be negative 5, negative 1, 3, 7, 11. And the thing here is that we really take advantage of the fact that all variables are expressed in similar manners in the sets of equations in terms of coefficients, the number of times it appears, and different things. And this won't always be the case. Sometimes you have to deal with the equations and make it such that it works out that way. But in essence, symmetry is a very important method to be able to solve systems of equations in general. So now we get our answer. Yeah, and so we solved it the same way. Okay, so now let's go a little bit into a sort of tip sort of area on how to use the methods that we discussed. Gaussian elimination, like I said, when you're trying to avoid fractions, use Gaussian elimination. Sometimes it's not easy to isolate variables. For example, when you have an equation like 2y, or let's say 5x plus 2y is equal to 7. I really don't think it's easy to eliminate, isolate something without getting fractions. I mean, it's not possible to to isolate something without getting fractions. And with fractions starts to get really confusing. Unless you're really comfortable with fractions, then go ahead and do the next method, which is substitution. So that is something you want to look into, whether to choose, depending on how comfortable you are with different things. I know for me personally, I am not very fond of fractions. And in order to avoid that, I would use a Gaussian elimination more when it comes to when there's like coefficients in front of the variables. But definitely substitution is a very powerful one in the long run. So in terms of substitution, like I said, if you can isolate the variable, use substitution. One thing I would pay attention to is remember to distribute, right? There's this very example right here, which is like 5x plus 4, which often in your rush might be written as, okay, 5x plus 4. And that is wrong. These are not the same thing. And so you need to make sure that you don't do mistakes of that sort. And like kind of like how we talked about the word problem and converted that into a system of equations. If we had written that a plus 3, for example, was 3s plus 3, that would have been wrong. We had to write it as, which is not equal to 3 times s plus 3. And that's equal to 3s plus 9. So these are definitely different. And so I think that's what you need to pay attention to in terms of also substitution. Graphing, again, like we have reiterated for the past examples, and graphing should be your last resort in terms of solving systems of equations. And for some reason, if you aren't able to solve your equation with the first two methods, then you could sketch a graph. But like I previously stated, it's often more correlated to use graphing when they ask for the number of solutions rather than the exact solution. And lastly, symmetry. Use symmetry especially when there are many variables in a similar form, because you can like add or subtract equations like slyly, very smartly, like we did for the last example, and try to avoid multiplication. I would say it's not the end of the world if you use multiplication, because sometimes things can work out very well, especially when you have something like 1 over x, like x plus 1 over x or something like that, and you multiply that by another x plus 1 over x. You can often cancel out stuff, because like that often cancels out with that when you like multiply it out, because you get x squared plus 1 over x squared plus what is it, 2? Yeah. So these kind of things are really like useful. Sometimes you can in multiplication, so it's not end of the day if you do multiplication. End of the world, sorry. And avoid common denominators. Definitely, you can multiply things out, but don't like try to make a common denominator. That just like waste your time. And unless you really think that it's going to help you progress in the problem, don't try to do common denominators, because it just gets too complicated. Yeah. Okay. And that's about it. So let's kind of preview our first example before we get into it, which we're going to get into in terms of solution in the next video, but I'll just quickly read over the question. So in the following 3x3 grid, A, B, C are numbers such that the sum of each row is listed at the right and the sum of each column is listed below it. So we have a sort of table right here, and they're asking for n. What is n? So just take some time, think about it, and we will go over the solution in the next